Half-lives. You hopefully have been exposed to half-lives before, the concept of a half-life. Half-lives are usually introduced when you're talking about nuclear reactions and nuclear decay. So half-lives are how we measure how long it takes for nuclear substance that is radioactive and undergoing nuclear decay, how long it takes for that substance to kind of start to disappear. Um, the general rule of thought, and we will talk about nuclear at the very end of this course, is it takes about 8 half-lives for something that's radioactive to be safe to be around. Um, so what is a half-life? Let's first start about that. Half-life is a weird concept. Half-life is the amount of time it takes for half of a substance to essentially decompose or to change into something else. Um, so um, it is a weird thing, and it really only pops up in like things that like financial like stuff, like the stock market, and then like nuclear reactions are also where it pops up. Now, most substances that are radioactive, their half-lives follow first order kinetics, but not all. So there are half-life equations for zero order reactions and second order reactions. So here's the half-life equation. The amount of time it takes for half the substance to change is equal to the initial concentration divided by 2 times the rate constant if you're zero order. And if you are second order, the amount of time it takes for half of the substance to change is equal to 1 over the rate constant times the initial concentration. Now, the interesting thing with zero and second order half-lives is that these half-lives actually depend on the starting amount of the substance. So the half-life actually changes after each half-life. The amount of time it takes for half the substance to decompose is not constant for each half-life. If you stop and think about it, zero order reactions actually, after the first half life, it speeds up and it starts to get a little faster because now I have, oh no, wait, I got that backwards. I'm so sorry. For a zero order reaction, after each half life, it gets slower. So the reaction actually slows down. The second half life would take longer than the first half life because after the second half life, I have less initial amount in there, and after each half life, it gets slower and slower and slower and slower. If something is undergoing second order like decay, it actually gets faster because after the first half life, I'm now dividing by like 0.5 or 50 instead of 100. And then here I'm after the second half life, I'll be dividing by 25. And after the third half life, I'll be dividing by 12 and a half. So it actually gets faster because I'm dividing by a smaller number each time. It actually speeds up. Here's the good news. I am not on the test going to make you do a zero or second order half-life problem. Okay, because most radioactive substances are first order kinetics, we are just going to work on the first order half-life equation. And it is this. It is the is 0.693 over K equals the half-life. We're actually going to derive that here in just a second. I'll show you how to derive that. Another way of writing that is it's the natural log of 2 divided by K is equal to the first half-life. So this is the one that you're going to want to put on your formula sheet. And you can actually derive this one from the integrated rate law for a first order reaction. Let me show you. So here's how this would work. The half-life is the amount of time it takes to get to half of that value. So half of A. So we could put a 0.5 in here, half of the initial concentration or over 2. So what we want we want to rearrange this equation for T1 half, right? So we're going to subtract the natural log of the initial concentration. And here's a crazy thing that happens with logarithms. When you add logarithms, you actually multiply them. And when you subtract logarithms, you actually divide them. So this actually, when I go to subtract, this actually becomes the natural log of 0.5 AT over the initial concentration of A. And then that equals half of the initial concentration, That equals negative K times T1 half. And then if we divide by negative K, you can see the initial concentrations cancel out. And we end up with the natural log of 0.5 over K. And then that's all to the negative 1 equals T1 half. And if we go back, you can see that if you take the natural log, okay, so now what we could do is we could take the natural log of 0.5. The natural log of 0.5 is negative 0.693. So now it's a negative times a negative 0.693 over K equals T1 half. And now that becomes positive. So the half-life for a first order reaction is positive 0.693 over K. So I would absolutely positively put that on your formula sheet. That's how you get the half-life for a first order reaction. Now here's where this is useful. If we know the half-life of a reaction, maybe somebody studied it, you can use the half-life to get the rate constant. Okay, so if you know the rate constant, you can get the half-life. If you know the half-life, you can get the rate constant. So let's take a look at how one of these reactions would work. Let's practice one of these guys. Let's see, do I have a practice one in here? I do. So what is the half-life of a first order reaction that has a rate constant of 0.271 seconds to the negative first? So let's use this new equation. T1 half equals 0.693 over K. I'm giving you K. You should be able to very quickly solve for the half-life. All right. So the half-life is equal to 0.693 over the rate constant, which is 0.271. Here's the cool thing. If we do 0.693 divided by 0.271, we get 2.56. 2.56 what? The units on that rate constant for seconds is the negative first. Seconds is in the denominator of a denominator. It goes to the numerator. This reaction would have a half-life of 2.56 seconds. So it would take, this is great news. If this is some super toxic radioactive thing, this stuff's going to be gone in no time, right? Okay, so it takes 2.56 seconds for half of the stuff to go away. Okay, general rule of thumb, it takes about 8 half-lives. And here's why. You know, so you start with 100% of the stuff, right? After the first half-life, you're down to 50%. After the second half-life, 25%. Third half-life, 12.5%. Fourth half-life, you're down to 6.25%. After the fifth half-life, 3.125%. After the sixth half-life, you're down to 1.5625. After the seventh half-life, you're down to 0.78125. And after the eighth half-life, you're down to only 0.390625% of the original amount. It's almost all gone. So this would be the good news. If it takes 8 half-lives till it's safe to be around, well, 2.56 times 8, it'd be safe to be around in 20.5 seconds. Okay, so that would be great news. Unfortunately, the stuff that is the byproduct of like medical waste or radioactive waste from a nuclear reactor, that stuff has a half-life of like 7 million years. So you do the math, 7 million times 8. It's not going to be safe to be around for a really long time, right? We're going to be long gone, okay? As a human race, probably, not even just, you know, us, till that can get dealt with. Anyway, next one here is going to be going in reverse. In this one, I want to know what the rate constant for a reaction is if it is a half-life of 26.4 seconds. Go ahead and solve for that. All right, so in this problem, we're giving you the half-life and we're solving for K. So here we go. Just algebra here, folks. 26.4 seconds equals 0.693 over that rate constant K. Multiply both sides by K. 26.4 seconds times K equals 0.693. Divide both sides by 26.4 seconds. And the rate constant equals 0.693 divided by 26.4. That caused to be 0.026, probably 36 figs, 0.0263. And that's seconds to the negative first. That seconds is in the denominator. So that's over seconds, or seconds to the negative first. Cool. All right, this next problem doesn't require a super long amount of time, okay? Or it doesn't require really any crazy math. It requires you to be organized and to write this out. If a reaction has a half-life of 26.4 seconds, so half of the substance is gone every 26.4 seconds, how long would it take for the substance to be down to 1/8 of its original value, or 1 divided by 8, down to 12.5% of the original value, right? 1/8 is 12.5%. Okay, so if you actually put that in your calculator, 1 divided by 8 is 0.125. 0.125 times 100 is 12.5. So I want you to see, can you write it out, right? So I would recommend you start, and you can do percentages. Start with 100%. How long does it take to get down to 12.5%? Or you start with fractions, right? And see how long it takes to get to 1/8. Go ahead and give it a shot. I'll go over it in a second. All right. Come on. Here are the two ways to do this, okay? You're starting with 100% of your stuff, or 1 out of 1. Then you go down after the first half-life to 50%, or 1/2. Then after the second half-life, we're down to 25%, or 1/4. And then after the third half-life, we're down to 12.5% of our original substance, or 1/8 of what we started with. So the key to this problem is it takes 3 half-lives. Well, if each half-life is 26.4 seconds, then 3 times 26.4 seconds is going to be the total amount of time it requires, right? So 3 times 26.4, that is 79.2 seconds to get to 1/8